Okay, guys, moving on to a new subject. We're doing contributing scientists, right? So we talked a little bit about this in the previous couple of chapters. We looked at the atomic emission spectra, and we looked at spectroscopy. We looked at all these things, an overview of the history of astronomy. We kind of talked a little bit about some of these scientists, but it's very important to see how the nature of facts changes with the definition of how science is done. And as we get a little bit more sophisticated and we refine what it means to do scientific pursuits and scientific research, we definitely change what it means to be factual. And it's important to note that in science, that the word fact does not mean what you think it means. It doesn't mean truism, okay? So we kind of think of the word fact colloquially or, commonly as something that is a truth, an absolute truth. But a fact literally just means it is something that can be verified. It's verifiable. If I could spell that correctly. Yeah. Something that is verifiable. Well, it means that I can see whether it is right or whether it is wrong, right? And sometimes things seem to be right for a while until we have more facts about it and then it's wrong, right? So maybe when you were a kid, you thought that, I don't want a spoiler alert, but maybe when you were a kid, Santa Claus was real and it was verifiable because you'd wake up December 25th and there'd be presents under the tree, right? But as you got older, more facts came to light and you saw that that was actually not correct, perhaps. Or maybe you haven't gotten to that point in your cultural evolution yet, or maybe you don't celebrate that holiday at all and maybe it was a really bad example. But what I mean is it was a fact for a long time in your life that Santa Claus was real, and it was something you could count on, it was something you could calculate and predict, and those are things that are verifiable. But as more facts come to light, you see that those the underlying mechanics of how Christmas worked isn't necessarily a magical man in a suit that's somehow compressing himself through a chimney, getting around the entire world in just maybe 10 hours and getting presents to every single family that celebrates Christmas, right? And that's kind of mean, right? Maybe you should drop presents in people's houses that even don't believe in him, right? Anyways, let's talk about the ancient Greeks. We talked about them a little bit. So, followers of Pythagoras, so this is, 3 to 5,000 years BC, believed that the earth was spherical, okay? So, we've talked about this in class before. You don't even need sophisticated satellites and high-tech technology to know that the earth is round. Pythagoras' followers believed that the earth is spherical for a lot of empirical reasons, and one of the main ones was just looking at ships on the distance. So ships on the distance. So we talked about this before on a flat plane. If you were here and you saw your friend, we'll go ahead and make him red friend. You saw your friend walking away. Okay, well, I can't make him walk away. But let's say he's moving this way. As he gets further and further and further, what does he appear to do? He appears to get smaller. Okay, he appears to get smaller and smaller and smaller and smaller and smaller. But technically speaking, you could use something like a telescope, right? You could use a little telescope. And you theoretically could see him and blow his image up to make him look bigger, right? No matter how far he went, you could make him look the same size, right, as long as you kept on magnifying the telescope. But what happens if your friend were to, say, go down some steps? Well, as your friend goes down the steps, not only would he get smaller as he gets farther away, but he would also appear to sink in the horizon, or he would sink down those staircases, and eventually he would fall out of view, and it wouldn't matter how powerful you magnify that telescope. Well, the ancient Greeks saw things like ships on the horizon. They saw the sun on the horizon, and they noticed that they noticed that as objects get further away, they do get smaller, but they also appear to sink, and that's something that's very, very easy to see. It doesn't require crystalline, weird, magnetic laser technology to be able to tell if the Earth is level all over the place. You don't need to do that. Okay. On the other hand, Democritus believed the Earth was flat, right? Plato and Aristotle thought the Earth was the center of the universe. And for a long time, these things were facts because they were observably true, okay? So because they were observable and they fit data that you could see, they fit predictions, that they were working systems for the time being. Okay. Aristarchus of Samos claimed the sun was fixed center of the universe. Okay, so we start having these different ideas about heliocentrism, geocentrism, anthropocentrism, which is the center, human beings being the center of everything, and a lot of anthropocentrism. Anthropos means human, like anthropology. Okay, anthropocentric, anthropocentrism. So anthropocentrism, in my opinion, is kind of the root of a lot of geocentrism, which is the center, the Earth being the center. If you believe human beings are all important in the universe, that we are an important, unique creation that the universe bestowed upon itself, then you would necessarily probably think that the Earth is probably the center of all that. And the Earth doesn't feel like it's moving, right? So that was something that Aristotle talked about, right? Aristotle was like, well, if the Earth was moving, things like dogs, birds, humans, he literally said something like this, would all be left in space if the Earth was moving, okay? They'd all be left in outer space. So what they lacked was a modern Newtonian physics understanding that if you are in an inertial frame, so an inertial frame, you have all the moving characteristics and properties of that inertial frame. So that's why you can be walking and drop something, and it doesn't just fall behind you, it travels with you, right? You can try this, right? You might say, like, well, I threw something out the window when I was driving a car and it flew backwards. Well, that's because there's wind resistance, homie. So, but if you were in a vacuum and you drop something, it's going to travel with you. You can even if you were, and this is kind of interesting to me, right? This is really, really, really interesting. If you were on a train, right? So you're on a train. So I'm going to draw like a flatbed of a train. Here are all the wheels, blah, blah, blah. I'm only going to draw like 3. Okay. And you were up on like a gigantic chair, maybe 100 feet up in the air. So this is 100 feet tall. You're on a platform. You were to drop like a quarter or something. Oh, it didn't work. So if I were to drop a quarter, and this train is moving super, super fast, like 60 miles per hour or something, a lot of y'all might think that as I'm moving, this quarter is going to fly this way, right? But no. If this train is moving at 60 miles per hour, or 60 meters per second, I'm used to doing the physics stuff, that means everything on the train is also moving at 60. That means this little quarter is also moving at 60. So when you drop it, it still has the properties of the moving train, so this will actually fall with you the entire time. Okay, so that's something that Aristotle didn't understand. Yeah, so that's really interesting. That's inertial frames that Aristotle didn't understand. But in the absence of these facts that were discovered thousands of years later, they had to work with what they had, right? It doesn't make them stupid. It doesn't make them any less genius than the modern people that have the wealth of knowledge afforded to them by their ancestors. It just means that they were ignorant of certain facts, right? And it's humbling in a way because we know that there are lots of things that we do know, but there are many more things that we don't know. And a good scientist knows that we learn things just to realize that there are more questions that we don't understand, right? So just keep that in mind. Our inquisitive nature is what has put us here in the first place. Okay, Hipparchus of Nicaea ended Aristarchus' theory, stated that the geocentric model better explained observations than Aristarchus. Okay, and you start looking at little systems of predictions of how we can do that. Okay, moving on. We're going to move a little faster. So let's talk about Ptolemy. He perfected the geocentric model, in quotes, perfected, because it's obviously not the model, right? In Ptolemy's model, the planets moved in circles. You call these epicycles. Make sure you get this down. This is the exam question. That moved on other circles, okay? Deference is what those were called, deference, okay? He predicted the positions of planets. He had really, really good eyesight, by the way, very good eyesight. And that's part of why his model was accepted so widely, is because he had such good eyesight and his visual observation, because he did these a lot without the aid of a telescope, so he was very revered for his eyesight. Okay, the Ptolemaic model was used for 1,300 years. Okay, what you need to get out of this, remember, is the epicycles. Okay, so here are the epicycles, and the deferents are the circles that they do on their epicycles. Okay, Hypatia of Alexandria. Okay, the first female astronomer, charted celestial bodies, lived during the rise of Christianity, and died because of her work and teachings. So a lot of people, they really believed in what they saw, right? This is sometimes what people are willing to die for. Is there something in your life that you are so certain of that you would risk your life and limb for? It's kind of crazy. A lot of us don't, right? We understand and accept a lot of facts in our lives because they're in textbooks, right? But just keep in mind that there are lots of different pioneers in history, and most of them are not necessarily pioneers of travel. They're not pioneers of like foreign lands. They're pioneers of new thought, right? Imagine being the first person to ever have a new thought that nobody else had ever had. Nicholas Copernicus. So you guys probably know about this guy. He became interested in astronomy and stated the sun was actually the center of the solar system. And he did this because of his stellar observations. Copernicus worked out his sun-centered system in full mathematical detail. So this is what we call heliocentrism. Not the mathematical detail, but heliocentrism just means sun-centered. Okay, helio is sun, center is center. Okay? By postulating only the rotation of Earth, Copernicus explained the motions of the heavens. And in fact, this is something we call Occam's razor. Okay? Where it is probably more likely that something is true if it simply explains something. Okay? If it is a more eloquent, simpler explanation of a system, then it is more likely that that is what is causing it. So if I walk into my kitchen in the morning and I see sugar all over the place and I see broken glass, I could assume that it was a bunch of gnomes that came in and decided to wreck my house because I didn't leave out my tribute of milk and cookies. Or I could see that my cats are covered in sugar and be like, oh, it must have just been the cats. One of those is a more fun answer. One of those is a perhaps more convenient answer for the cat, but it's not likely. So it's probably a better idea to go with a simpler thing. It doesn't work all the time, but Occam's razor tends to be true for a lot of things in science. Okay, Copernicus is credited for stating the universe has no center, the Earth and Sun distance is very small, and the Earth's rotation accounts for the daily rotation of the stars. Okay, he was true about a few of those. Unfortunately, out of fear, Copernicus delayed publication of his findings. So he has in his Principia, so it's called Principia. Let's see. Principia Orbium Coelestum. Okay, so it's a principal mathematics of the celestial orbs, right, and spheres. And so what he said in the beginning of his thing is he has a disclaimer to the state being like, the church, that this is actually just a mathematical practice book. This is all theoretical, and he has the utmost respect for the Catholic Church's findings, and it's not meant to be disrespectful, right? And even so, even with that disclaimer, he did this posthumously, which means after death. Okay, posthumous. Posthumous. Like if you put something in the ground to decay, it becomes humus, right? Not hummus, the delicious chickpea bean paste, but humus. Okay. Now, these are the things that he was going against right here. So here's the Ptolemaic model. And the Ptolemaic model, Earth's in the center. And to account for things like retrograde motion, which is the apparent, so every night if you were to track the moon, it might look like it's doing this. Boom, boom, boom. So Monday, it might be here at 12 o'clock at night. Tuesday might be here at 12 o'clock at night. Wednesday, Thursday, Friday, but then a couple months later, all of a sudden it's here. Oh, whoa, and then it reverses throughout the year. This is called apparent retrograde motion. The Ptolemaic model had a really hard time explaining that, so that's why they had to come up with this very complex epicycles and deference, whereas putting the sun in the center very eloquently gets rid of that, because some of the planets are moving slower than others. It's kind of like when you pass up a car when you're driving on the highway. It appears to be moving backwards, but then they could, as you slow down, it could speed up, right? Or if you guys were both going in like a turn like this, right? See how like at one point it looks like I'm ahead, and then all of a sudden as I turn, kind of the one on the outside kind of passes me up a little bit. So that's very easily explainable when you put the sun in the center of the universe. Okay, contributing scientists post Copernicus, after Copernicus. We're going to watch a video on this today. Okay, got Giordano Bruno, an Italian philosopher with ideas in science where he rejected geocentrism and whose ideas were beyond Copernican heliocentric model. Okay. It's worth noting he didn't really have a lot of mathematical reasons for this. He was just kind of he thought it was the godly position of the sun. But it's interesting either way. Okay, Bruno exceeded the Copernican heliocentric model by stating that the universe is infinite. All suns are capable of having their own planets, and other planets will contain animals and inhabitants. I mean, he's just extending logic. But this also makes the assumption that Earth and life is not necessarily unique or rare. It's that if the universe is made up of the same stuff as here, it's just probabilistic that we would have other life-like, Earth-like planets and qualities elsewhere. Okay. Throughout his life, Bruno championed the Copernican system. He opposed the church and refused to recant, which means to go back on his claim. His philosophical beliefs throughout his 8 years of imprisonment. On February 16th, 1600, the Roman Catholic Church executed Giordano Bruno. I think they set him on fire. Tycho Brahe. Now, this guy had some good eyesight. Okay. Danish astronomer who made precise measurements, precise with the unaided eye, understanding the motion of planets. Look up what this guy's nose looked like. I want you to Google that. Tycho Brahe's nose. So Brahe's nose. Then I also want you to see how did he died. How did he died? Yeah, it's very interesting. Okay, Brahe's contributions included the following. He proved that SN 1572 was a distant star compared to other stars, and he did that by looking with his eyes, and he noticed that it didn't seem to move very much. Found that comets are further away than the orbit of the moon and not atmospheric aberrations, and you can do this just by kind of looking at things called occlusions. Okay? So if something occludes, which means blocks, right? Something blocks the side of another thing, it stands to reason that it must be in front of it, right? So if you're seeing comets pass, right? Let's say I got the moon right here. Okay. Okay, that is weird. Don't know why I did that. Sorry. Okay, let's say this is a comet. It's a really ugly comet, but whatever. Okay, now if the comet were to pass in front like that, you know that the moon is further back. But if this were to pass behind it, let's see if I can move this around. I cannot. I can't move it anymore. Okay. Well, if it were to pass behind it, you know the moon must be closer. That's really all there is to it. Okay. Brahe laid the foundation for Johannes Kepler to discover the laws that govern the motion of the planet. So Kepler studied with Tycho Brahe. Okay, let's talk about Kepler. He was German. He was an astronomer who discovered the three major laws of planetary motion, and you're going to want to write these down. Okay, Kepler's law, the first law, the planets move in elliptical orbits. So with the Copernican system with the sun in the center, one of the major flaws is that, so with Copernicus, they had circular orbits, and it didn't fit the data incredibly well. So Tycho Brahe's stellar observations were a little bit more popular, and it gave a lot of credence still to the idea of the geocentric model, because at least there was a really complex but working system that explained where stars and planets were on a nightly basis. But Copernicus having circles really didn't fit this too well. But as soon as we move over to ellipticals, so Kepler started using ellipticals, which are kind of like these oval shapes, all of a sudden stellar observations start working out a lot better. Okay, sun is at the focus. Okay, so there's a focus, there's a focus. There you go, here's some ellipticals. The time, so this is the second law, the time necessary to traverse the arc of a planet is proportional to the area of the sector between the central body and that arc. So in other words, so the time is equal, or is proportional at least, to the area covered. So if I travel across an arc, the area that I cover is proportional to that time that I traveled. So that's the second law. Okay, 3, planets that are further from the sun move slowly, more slowly than the ones that are closer. And this is angular momentum, by the way. Okay, Galileo Galilei. In 1610, the mathematician and astronomer Galileo Galilei published major findings of his astronomical observations with the telescope he built. So keep in mind, all the astronomers that we've been talking about have been doing this without being able to look at them very closely. They're just using their eyesight. That's crazy. Like, I have crappy eyes. Like, I would never have been able to do most of this stuff. Proving that they were not everything orbits Earth. He prompted the Copernican view of the sun-centered universe. Okay, so se muovo is what he reportedly say at his trial when he got tried by the Inquisition, the church, for being a proponent of the sun-centered theory, right? But when you start looking at the moons of Jupiter and things like that, you can see that, oh man, these things are actually Jupiter is occluding its own moons. They're not traveling around the Earth. So that was one of the things that he saw that kind of promoted the idea that, if not everything is orbiting the Earth could also be orbiting something else. Okay, so his contributions. He contributed to math and science and other things than besides just gravity. Like he had the famous rolling the cannonballs and marbles down the ramps and stuff like that. He also discovered sunspots on the sun with his telescope. So he looked into the sun. Don't do that. I'm just kidding. No, it's fine. He's probably fine. Finding craters on the moon. So he found out the moon is actually a Swiss cheese. Just kidding. And he developed the Galilean telescope. By the way, all the craters on the moon basically have the names of like all these scientists you're learning about right now, like Kepler and Newton, Galileo. We named them later. These little craters we call mare, which means sea in Italian or Latin. Okay, and also the side that we face the moon, it's geosynchronous or synchronous rotation. Okay, we have synchronous rotation. In our case, it's geosynchronous because it's synchronous with the Earth, right? Which means the rate of rotation matches the rate of revolution. So rotation equals revolution. So the time it takes to get around the Earth is the time it takes for it to do one full spin, which means we're always going to see the same side of the moon. You ever thought about that, did you? Because you only think about yourself. If you were to look at the other side of the moon, or the dark side of the moon, it's way, way more full of craters and damage. It is one of our greatest protectors. It protects us from a lot of different asteroids and meteors. Not all of them, but that's pretty interesting, right? Because we always see the same side. The Earth is also protecting that face of the moon as well. Cool, right? Goes both ways. So more contributions. He supported Copernicus by finding that the moon was round with craters and not flat. Venus had phases similar to the moon. Anything that's closer to the sun than the Earth was going to have phases to us. Okay, we're going to see phases because we're going to get in front of the object. We're going to occlude the sunlight from the object, so we will see phases. We're going to cast a shadow on whatever object we got there. Okay, cool, right? He discovered several of Jupiter's moons, aka the Galilean satellites, Io, Europa, Ganymede, and Callisto. And those all have some very interesting properties that we'll study this year. Okay, some more people. We've got Isaac Newton. You know about Isaac Newton from the Cosmos. He gave us the reflective telescope, so not just an optical glass, but he also put mirrors in there. Okay, he looked at the motions of the planets. He came up with gravity by creating differential calculus. That's crazy, right? He invented a discipline of mathematics to help prove gravity. The universal law of gravitation, big Fg equals big G times mm over r squared if you've taken physics. He did the color spectrum of light with the prism. There's calculus, and he did his 3 laws of motion, right? Object in motion stays in motion, object at rest stays at rest, A equals F over M, and of course, the last law, forces all come in pairs, right? For every action, there's an equal and opposite reaction of the same type of interaction. So in other words, if gravity pulls on you, so here's Earth's gravity, the Earth pulls down on you. If you're in outer space, you're a spaceman or spacewoman person, helper thing. So this is the Earth pulling down on you. It's gravity. Well, guess what the equal and opposite reaction is? Yeah, that's right. It's weird, right? You are pulling back up on the Earth with more or less gravitational force. You are pulling on the Earth with the exact same gravitational force. That's Newton's 3rd law. And that's kind of weird, but it's true. And I can explain that another day. Albert Einstein, he came up with his general theory of relativity, the speed of light. He calculated and quantified the speed of light a little bit better. E equals mc squared. And there's actually like a nice little historical tangent you can go off on of different scientists throughout history. As early as like the 17 and 1800s trying to come up with the speed of light and like their interesting devices they had. So some of them are pretty ingenious, like spinning, rotating mirrors and lights from really far away. Gravity and light relationship, modern quantum physics. So it's worth noting that Albert Einstein really didn't understand or really like quantum physics. He thought it was very spooky. He called it spooky physics. He came up with the idea of space-time and the photoelectric effect are all attributable to Albert Einstein's findings. Okay, here's some other notable contributors, and there's hundreds more, but in the short span of time that we have, here's some of the big ones. Edwin Hubble, you learned about him from the previous chapter, Light and Telescopes. He came up with the Hubble constant, which looked at the expansion rate of the universe. Okay? Clyde Tombaugh, He discovered the demoted dwarf planet Pluto, which I think as of recent is back to being planetary status just out of cultural importance. Carl Sagan came up with the first Cosmos series, and he made astronomy popular in the 70s and 80s. He was a professor at MIT. Neil deGrasse Tyson is probably one of my favorite educators of all time. He makes astronomy popular today. He's actually on his second season of Cosmos after about 8 years of kind of just letting the last one kind of simmer in the public sphere. But he has a podcast called Star Talk Radio. It's very interesting. It's a wide range of topics that isn't just about space. He talks about like the frontier of pop culture and the human condition, and also science and why it's important to us. And he's just a very good science communicator and educator. Then Stephen Hawking is known for his work involving black holes. One of the most interesting things that he came up with is the idea that black holes will dissolve or evaporate over time. They evaporate over time, and they eventually just let their matter loose on the universe again. But it takes trillions of years to do that. Okay, so some questions you should be able to answer. Why do you believe Ptolemy's model was accepted model for 1,300 years? Again, we talked about that a little bit, the cultural and scientific observations, the cultural importance of human beings. How would science be different if the church had instead welcomed ideas like the heliocentrum early on? Okay? And 3, how did Galileo's telescope revolutionize science and humanity? And what I want you to kind of think too, question number 2, is what beliefs do we hold today that you think may impede scientific progress? Or what do you think we will not believe in 100, 200 years from now? What do you think will be different about human beings? And how do you think that will affect our ability to learn and quantify and assign inherent importance on things in the universe?